Damon Woods here from Integrated Design Lab. Thanks all for joining us. Thank you especially to Idaho Power, who sponsors this program and helps us all become better energy modelers. Tim, thank you very much for joining us today. I'm sorry we can't give you lunch in person, and appreciate all that you've done for BSUG, and thank you for presenting today. So I'll give a quick intro and then I'll turn it over to you, Tim, to take it away. But I did want to mention that our next BSUG is going to be coming up on November 18th. So I'll be talking about schools, COVID, ventilation, and using energy models for that, specifically looking at long-term energy costs of different HVAC systems and how we can model different classrooms in a few different situations, including Open Studio as well as other programs like eQuest. A couple other pieces of front matter. There will be a poll at the end, so please let us know how we're doing and how we can serve you better. If there's topic ideas you'd like to see in the future, let us know. It's also how we give out prizes thanks to Idaho Power. So if you're in Idaho Power service territory and you're attending this live, great, you've got a chance to win. Tim can speak on this. I think he's got personal experience from winning some prizes in the past. And we'd love to, meet with you in person once all this COVID mess is behind us. But for now, it's my great pleasure to introduce Tim Johnson, who joined Cushing Terrell in 2007 and has continually been really a champion locally and in the broader simulation community for building design, looking at strategies for achieving LEED certifications, Architecture 2030 goals, and net zero energy consumption. I certainly look to him on the forums and just over email because he's such a great expert in Open Studio usage. He focuses on using simulated and measured data to inform design decisions and influence industry trends while optimizing investments. He's also a licensed mechanical engineer who leads the Boise mechanical engineering team at Cushing Terrell, regularly designs elegant and efficient buildings across several market sectors. On top of that, Tim is just very generous, just personally and with his knowledge and being willing to share it with us. So I'm grateful for that. He's also very involved in our local ASHRAE chapter. So it's my great pleasure to introduce Tim. Tim, I will let you manage how you want to field questions, whether that's through the chat box or have people unmute or hold them to the end. But I think my intro time is done, so I'll turn it over to you. Thank you.
Well, Damon, thanks. I appreciate that. And as far as questions go, I'd say I think everybody has the ability to unmute, so feel free to go ahead and do that and interrupt me. I'd rather we talk about things that are important to the group than me get through my stuff today. So with that, let's kick it off here. Looks like we have a pretty good crew with a lot of varied backgrounds, so I'm interested to hear from everybody online too. So here's kind of the summary of what we'll talk about today. There's a number of reasons that typically push us into the performance path rather than prescriptive paths for energy code compliance. So we'll go through some of those. We'll get into the energy code, the nuts and bolts there. I thought about, rather than you guys hearing from me, maybe I'll just read the straight energy code to you, but figured I can't tell who's sleeping and who's scanning Facebook instead, so maybe we'll keep it brief on the energy code stuff. Then we'll move into a few case studies, talk overall strategy on simulation in terms of how it relates to projects and getting things done correctly. And then some of the industry trends I'm seeing out there, and wrap it up with some conclusions. So first of all, when we're talking the performance path, essentially what we're talking about is an energy model, whereas typically what we're seeing is ComCheck or some other sort of prescriptive path where we're filling out paperwork. We're talking about 8760 simulations tested to ASHRAE 140. I listed the software criteria there. And then another wrinkle that's been interesting in the last few years is Appendix G from ASHRAE 90.1. Used to be that was definitely separate from code compliance, but those are starting to blend a little bit. So we'll talk about that a little bit, and yeah, let's get rolling here. So why would we model? And I think the obvious answer is because we're really, really ridiculously good looking, but there are obviously a few other reasons beyond that. Here's the picture of our energy modeling crew there and doing some modeling. Finding the best value, I think, is at the heart of it. And with our energy models, we're doing true value engineering here, trying to figure out what has the best performance, what is the least cost, and trying to identify those for the owner. But there are a few things that really drive us into the performance path. One of those is too much glass. I think we've all seen the glass box buildings, especially in these a lot of the high-rise buildings. They're just 30 stories of glass, and that doesn't comply with the prescriptive path. So that'll drive us into performance path. Economizers, have been seeing that quite a bit lately, where we're splitting ventilation requirements from space conditioning. So we'll have a dedicated outside air system that isn't really designed for economizers. Envelope insulation, we see that especially in thermal mass. We're trying to get the benefits of CMU or something like that, and we don't want to fur out the walls. Green building certifications, a lot of times if we're doing a green building certification lead or others, we've already done most of the paperwork to do a performance-based compliance. So we'll just roll that into that. So let's get into the code stuff. First, a quick reminder that if we're complying with energy code, we've successfully designed a legal building, right? This is minimum legal requirements we're talking about here. We're talking IACC and ASHRAE 90.1 primarily, but I'll touch on the federal government has its own performance standards based on ASHRAE 90.1, 30% savings better than ASHRAE 90.1. And you know, pay attention to state and local codes. There's a lot of other different types of codes out there and little tweaks to IECC and 90.1 that you need to be aware of. Here's a map, and looks like it needs a little bit of work. I took a look at this last week, and Idaho is still a little bit behind. But we know better than that. We also know that there's a code update coming in January where we'll be adopting the 2018 version of the IECC. So anyway, with this map, you can see the diverse energy codes across the country, and all of them have slight tweaks, amendments to the codes. A lot of cities or counties will have codes, so make sure you know who your AHJ is and exactly what is required from project to project. And again, those are legal buildings. Let's set our sights a little bit higher. I suggest the 2030 challenge. That's something we strive for here. Pretty aggressive goals, probably something we're not going to hit on every single project, but something to aim for where we're carbon neutral by the year 2030. Okay, so we'll start off with IACC. You crack open the IACC, go to the commercial building section, and there's 3 code compliance options. And actually the first one right out of the box is ASHRAE 90.1. And we're going to talk about 2015 and 2018 versions of IACC. They're really pretty similar in terms of their structure. So 90.1 essentially gives you 3 more alternatives. So first one is prescriptive, and there's some nuances to the prescriptive that aren't exactly all the same, but as a general rule, we've got the prescriptive path with ASHRAE 90.1, and you can do that through ComCheck or however you want to accomplish the paperwork there. Then there's the Chapter 11 energy cost budget. That requires an energy model, and that particular chapter really hasn't seen much in terms of updates in several years. So that's kind of the standard that we talk about in terms of the performance path. There's also Appendix G, and as of the 2013 version, you can use that for code compliance per an addendum. And in the 2016 version of ASHRAE 90.1, it's been fully adopted. And when we're talking performance compliance, it's not necessarily a free rein to do whatever you want with your designs. There's still some mandatory sections. And I'll go through those in a little more detail, but just keep in mind that, that there are those mandatory things to look out for. IACC has a fairly similar structure where we have the prescriptive path, which we're all fairly familiar with, I think, if we've been in the design business for a while. And then there's the, you got to pay attention to the additional efficiency. That's something that also gets missed. A lot of times LED lighting will get us there, but there's a number of different paths, including dedicated outside air in the additional efficiency. If you do want to go performance path in IECC, we look to section 407, and that also has its mandatory requirements, and it also requires that that our performance of our proposed design is 85% of the design building energy. So we have to save essentially 15% energy compared to a minimally code compliant building. So here's that in graphical format. You can see all the 5 essentially paths that we have to deal with in IECC territory. Also keep in mind the variations from jurisdiction to jurisdiction. All right, moving into 90.1, which is the first one we see from IECC. The mandatory provisions are air leakage. There's a couple of ways to do that. You can test the whole building, or you can do it by material and assembly. Mechanical systems, there are certain efficiencies that we have to work in there. Lots of tables for that. And then on the control side, there's certain sequences that we actually have to provide for various systems. Water heaters are usually not too much of an issue. The one that I find to be the biggest sticking point is Chapter 8 and the automatic receptacle controls. On certain space types, we're required to automatically control 50% of our receptacles. And that can be kind of a costly thing and kind of a nuisance to some owners, not knowing that their receptacles are going to shut off at certain times of the day or when unoccupied. So something to keep in mind if you choose the ASHRAE 90.1 path. Also, lighting controls included in the mandatory provisions, and electric motors. IACC is pretty similar, but does not include the receptacle controls. We still have air leakage, efficiencies, sequences, etc. And also worth considering that daylight controls are included on both of these, I believe. Some of the notable exclusions that you'll find in the IACC are on the building envelope side. We do not have to comply with window to wall ratio. I mentioned the glass box. That is not a requirement that we meet the window to wall ratio. 40% is kind of the upper max, and that includes some exceptions. And then economizers, they're not part of that, and interior lighting power density. So those are some of the knobs we can tweak with the energy model. One thing to consider, and I've heard brought up at other performance path presentations, is what are the long-term impacts of not meeting the prescriptive code? For example, if we were planning to do condensing boilers and LED lighting anyway, is that an excuse to cheapen our envelope, essentially? I think most of the time that's not the case, but just something to consider there. All right, IECC section 407, which outlines the energy modeling requirements for performance compliance, and chapter 11, energy cost budget from ASHRAE 90.1. Those are essentially identical, and you'll find that even some of the wording is exactly the same. So those are equal paths, and in my mind, just keep in mind that the IECC requires that 15% saving. So here's an example of what you see on the HVAC side. And a lot of us are used to lead modeling with Appendix G. where our system type is based on the size of our building, type of our building, climate zone, etc. The Chapter 11 or Section 407 from IACC is based on the system that you're using. So if you use an air source heat pump, you go to air source heat pump and you follow the flow chart there. And similar, even if you were using, say, a ground source heat pump, you would go to water ground, go to heat pump, and system 6, which refers us to this table. Outlines all the different system types. So system 6 would be a water source heat pump, except it would have DX cooling and fossil fuel boiler as the source there. Here's the Appendix G version. Similar in terms of number of systems, but you'll see that the way we choose them is different. Public assembly, heated only storage, retail, non-residential, etc. But it leads to similar systems. But in this case, with Appendix G, I've found in the past that, for example, if we're doing a larger building that would drive us into a packaged VAV reheat, and our actual system is a dedicated outside air system with a zone heating and cooling system, we can take quite a bit of credit for the system selection, which is not the case with the energy cost budget. Okay, looking into Appendix G, as I mentioned, it was kind of rewritten for the 2013 in the 2013 addendum, and now as part of the code in 2016. This is now a fixed baseline, which has been something that we've been targeting for a number of years. The moving baseline is kind of a pain for setting up simulation baselines and trying to keep track of what's going on every year. Now it's a fixed baseline with a building performance factor that we apply. So here's the equation for calculating that, and performance cost index is the value that they're using. And at the bottom, you see the equation there. The performance cost index is calculated as essentially the total energy minus plug loads times a building performance factor. And then you add those plug loads in separately and then divided by the total. And this is energy cost, not energy, something to keep in mind. And then the proposed is essentially the same formula with that building performance factor removed from the equation. So it's definitely a different way of thinking about Appendix G. So to give you some context, here are those building performance factors, and it's not quite a direct relationship to energy savings, but it's essentially the amount of energy savings by HVAC and lighting and all the what they call regulated uses. So, for example, in office building, we're allowed to use 61% of the energy that would have been allowed in 2004 energy code. And so some of these are pretty aggressive, 50% savings in schools relative to 2004. And I'm curious to hear thoughts from the crew online, if anybody's had experience with these building performance factors. So far, we've been finding them to be fairly aggressive and difficult to meet. We found the energy cost budget to be a little bit easier to comply with. But if you do have comments, feel free to hop in here and interrupt or leave something in the chat. So here's a glimpse into the requirements of Appendix G. The ASHRAE 90.1 standard has tables like this that I think most of us are familiar with, but now these tables also exist in Appendix G based on that 2004 ASHRAE 90.1. So instead of a 13 SEER package unit, our requirement is 9.7. I'm getting some comments that everybody else is, or others are starting to struggle with the PCI too. Appreciate the comment there. So yeah, definitely a new way of looking at things, something for everybody to get used to, and hopefully we can continue these discussions and and have some impact on what that PCI number ends up being for a lot of these facilities and climate zones. All right, in terms of documentation, it's not super well defined. ASHRAE put out a tool, an online tool with a link there that helps you fill out some of these forms. This hasn't been updated since the 2010 version as far as I can tell, but not much has changed in terms of what needs to be documented. So you can use those. We've taken these forms and essentially integrated them into our Excel results. So anytime we're compiling energy modeling results, we can easily fill out these forms. There's also other things as far as inputs that we need to include with the documentation. Some of our envelope, lighting, HVAC parameters, just so the code reviewer knows what we use for inputs and they can compare that against the construction documents. Annual energy by end use is something they want to look at. Proposed versus baseline obviously is kind of the key indicator, and again, this is cost, not energy in most jurisdictions. At this point, in most jurisdictions, there's no requirements for the energy modeler to be licensed in any way. I have seen a couple places, I think Seattle is one of them, that are looking for a BEMP, ASHRAE BEMP certification or a PE AIA license. Input and output reports from the software is something that 90.1 alludes to. And I think that probably depends on jurisdiction too. I think a lot of the jurisdictions we work with, they don't really care to see hundreds of pages of results, but somehow condensed results are also handy. And then explanation of errors. I think a lot of us are used to dealing with that in LEAD. If you have a whole bunch of errors, that's a red flag to reviewers. So being able to explain maybe where the energy model or the errors popped up and why that doesn't affect the accuracy of the simulations. All right, so here's if everybody's still awake, I hope everybody's still awake after the code specifics there. Hard to tell. But here's an example project we did a number of years ago for, I think it was the GSA. And this is a building where they have offices around a core data center and a lot of internal loads with the data center. And even though it was cold outside, we found that there really wasn't a lot of benefit to adding a bunch of insulation. So looking at, it was a major renovation of an existing facility. So we found the cost of the insulation to add a couple inches of insulation was a little over $100,000. And the energy cost savings we get from it was about $260. So the simple payback is 413 years. So this is an example of a time maybe where we'd want to invest that extra money into HVAC systems or lighting upgrades or controls or that sort of thing. Thermal mass is one that comes up quite a bit. Some of our clients really like the thermal mass for its durability and some of its performance characteristics. So you'd want that, the thermal mass or the exposed concrete on the inside and the outside. And to comply with energy code would require furring a wall out to add some insulation or some amount of additional insulation on the interior or exterior, and you'd lose your durability. So we've been looking at ways we can upgrade HVAC and lighting and still keep the performance characteristics of the CME walls. So here's an illustration of what that looks like. If we start from essentially an R value of 1, going all the way down to about an R value of 20, there's definitely diminishing returns in terms of heat transfer through that wall. And right here at about 11 is where code currently requires us to be in Idaho. But about 10 is kind of your typical integral insulated CMU block. So if we go just below code, there's really not a lot of difference in heat transfer. So that's one place we've been seeing the performance-based code compliance modeling coming in handy. Economizers, I already mentioned, are a big one. There have been jurisdictions out there allow exceptions for dedicated outside air systems, not needing to comply with economizer requirements. Haven't seen that in IECC or 90.1 yet, but it seems like that's something that is being discussed. So currently IACC and 90.1 lets you have 54,000, essentially 4.5 tons of cooling in an individual unit before an economizer is required. And IACC has a limit to total building cooling capacity of 300,000 BTUs. So if you are over either of those, an economizer will be required on your equipment. And we have found if we're doing dedicated outside air with heat recovery, that generally performs very well compared to a baseline. Too much glass, IACC lets you have 30% without exceptions. There are exceptions to let you get up to 40, but it doesn't apply to, I think it's floors above ground level, essentially. 90.1 lets you start at 40% and has a few additional exceptions. So pay attention to that. And if we are going with a lot of glass on a project, we'll know at the beginning that there needs to be an energy model to show code compliance. So now we're going to get into strategy, and I've always enjoyed whitewater, so I like to use that as an analogy here. If we're going into a river trip or something, we need to know our path. We need to know what the obstacles are in front of us, and we need to know where to go in the process of the project or the trip. So things we need to think about are, what are the parameters that make a difference? Let's figure out those that have the biggest impact, focus on them. And let's not wait for the designers to make these decisions for us and then react to them. Let's get out in front of things and start to influence the design, not stick to mechanical engineering or electrical engineering or whatever it is. We need to be able to look at the whole picture. And I alluded to this earlier, but this is true value engineering. A lot of times value engineering is really just cost cutting, where we come in at the end of the project and try to get rid of some cost. But here we're trying to figure out where the greatest value is and put our money into that, rather than you know, bulking up the insulation when maybe that isn't necessary. And we really don't need very much to get started. This photo at the bottom here is of a sketch from an architect, and we really don't need more than that. We can probably even get started with less than that. Just an idea that gives us some idea of the magnitude, where's the project located, that sort of thing. And ASHRAE came up with the standard. You take that P off there, it's no longer peer review. It's a standard now, ASHRAE 209, that outlines the different energy modeling cycles. And 1 through 7, I believe, are essentially in the design process, and beyond that is construction and post-occupancy. And I think this gave us a great guideline to get started with. I tend to find this a little bit complicated. It's hard to keep track of each of the different phases. And so I've, for my simple mind, I've separated these down to essentially 3 categories, where we've got the conceptual design, design implementation, and operation. So we've turned this this idea of a river trip into a graphic we can refer back to, where we're starting out at the headwaters, where anything can happen. There's all these different ideas coming together, and we're looking at everything under the sun. And this is where we can have the greatest impact on design, and it also has the lowest cost, the impact to the project, where our explorations are quick and they're cost effective. And as we start to move on, we're exploring, we're seeing what the the climate allows us to do, and then we can start to think about reducing the load on the building. Which way is the building oriented? What are some of the forms that we want to explore? What does the envelope look like? Are there passive strategies, that sort of thing? And once we've reduced the load, then we can start thinking about systems, HVAC systems. So really early on in a project, I think we've seen that McLeamy curve at these presentations a number of times, but the idea is essentially front loading this design. We spend a lot of our time up front developing this concept, and that's where we leave the headwaters section. We've got this concept, and it's our kind of our compass for the rest of the project. It determines our goals for the project, some of the systems that we've already decided are best, and we can use that to start to put lines on paper and really document the details of the project. And then once we've done that, we can refine our systems and then document them for code compliance or green building certifications or whatever the goal might be, utility incentives. And then after that, I believe in the importance of checking in on your designs. How did they perform compared to what you expected, and using that data to calibrate your future predictions. So we'll go through this process kind of step by step. And this one from the Energy Center Wisconsin, I believe, a number of years ago, really helped solidify some of these concepts for me. We talk about initially reducing the energy demand. We start off with a minimally code compliant project or a building, and we find that some of the energy measures, they will save us energy and really don't cost much extra. You know, I think one example right now is lighting. We can beat code pretty easily with lighting. It's just kind of a no-brainer. And so as we move along down the curve, we've got some pretty proven measures. We know these things work, and we can apply them to each building based on the application. But as we move down the curve, it starts to flatten out a little bit. And the benefit we get from additional cost starts to diminish. So at that point, we really need to start looking at renewables. And in the past, we used to be able to get there easily with efficiency only, but it's coming time to really start paying attention to the supply side. And it's a similar concept on the supply side, that initially there's some infrastructure costs. Let's think in terms of PV. You know, you need to figure out the net metering situation. You've got some structure. You need to connect it to your electrical service. But as the size of the array goes up, there's some economies of scale, and the cost per watt starts to go down. But then at some point we run out of room on the roof or wherever we're stashing the PV array. And so we need to move that array elsewhere to meet our targets. So what it boils down to is there's a sweet spot that we're looking for of efficiency and energy production. So keep that in mind as you're setting goals and looking at different energy efficiency and generation ideas. So first off, we start off with the climate. And I really like to look at psych charts. When I show these to architects, they start glazing over. I can see it pretty quick, but it shows you the entire 8760 years worth of data in one glance in terms of temperature and humidity. And so we can start to see if this is going to be a heating dominated climate, a cooling dominated climate. What is the humidity like? Are we going to have to dehumidify? Are there opportunities for evaporative cooling? Do we need to humidify in the winter? You know, what are the things we see right away before there's a building? We can already start to make some of those assumptions just based on the weather data. I think wind is something that's often overlooked too. Just looking at a quick wind rose gives us a good idea of where the wind's coming from and how can we react to that with a building form, and where might outdoor spaces go, that sort of thing. So this is an example of a project we did a number of years ago where we're doing this sensitivity and load reduction analysis. And what it took was sitting down with the architect, and he'd say, all right, we like this north-south orientation. How does that perform energy-wise? And I would show him the big loads associated with that, and then we'd say, all right, let's look at east-west. And it was kind of a one-by-one type of process where we'd we're essentially reacting to ideas. With our technology these days, this is Ladybug Tools. Ryan Schwartz presented on this a couple months ago here. We have the ability to look at a lot of different options at once, and we can build these into scripts and let the computer do the work for us. And so what we get is something like this. This is a Design Explorer from Thornton Tomasetti here. But this was a project where we wanted to see how much glass we could get into an office space and still comply with code. Well, this is definitely not a code compliance level model. We could start to look at the impact of the envelope on the energy cost. So all the way on the right, we have energy cost savings, which is really the end goal here. We're trying to have positive energy cost savings. So anything above 0 complies with code, anything below does not. And that's just looking at envelope measures at this point. So we take that, and we eventually decided on a quantity of windows and orientation and things like that. And we found that we were a little bit limited in what we could do with the amount of glass. So if we are going to do that much glass and we're going to go with the performance path, how do we get there? So we looked at solar heat gain coefficient of the glass on each exposure. We looked at shading devices, what their depth might be on each exposure. And really quickly, when you start to add up all these variables, you get hundreds of options. So this tool really lets us look at all the different options at a glance, figure out which ones comply with code, and throw out all the other ones. We can essentially start from the end result and work our way to a design. So once we've started or really dug into the envelope and reducing the load as much as we can, then we can start to look at systems. And I've seen a lot of times where we've got this heating dominated climate and the focus is on cooling systems. And I'd really encourage you to consider where that energy is being spent and what we can really do about it. Each site will be different, and also consider different sources. Ground loops are an interesting one. The cost is definitely something to consider, but when we have extreme climates, the heating and cooling can be much more efficient using the ground as a heat exchanger for us. Similar story on the renewable side. Rather than guessing at orientations and running one by one to see what tilt, what orientation is going to work best for our climate, let's just run them all. And pretty quickly we can get that chart and see what the D rates would be if we, for example, change the pitch or the tilt of the array, or if we pointed it southwest instead of due south. So I'd encourage you to simulate rather than guess whenever you can. And then bring it back to a life cycle cost analysis for the owner. A lot of times owners have a tight upfront budget, but there's ways that we can show the benefit over the long term in terms of maintenance, installation costs, that sort of thing, to kind of sell the idea. And sometimes even if we can show that a certain system will save a lot of energy, we can trade off. Maybe we don't bulk up the insulation, we put the money into the HVAC system or something like that. But it is important to consider what your client values the most. If it is the long-term energy benefit, or if it's, carbon has been coming up, or if it's strictly first cost, let's make this as cheap as possible. Once we have systems, so we're past the first step in the river map there. We're now onto the design implementation. So now we have all of the big concepts essentially worked out. It's time for us to work out the bugs. So let's take a look at the HVAC systems. How are they operating? Can we tweak the economizer controls? Should we control based on enthalpy or dry bulb temperature, for example? How about heat recovery? Are there times where we need to be turning off the wheel so we can economize, or bypassing it altogether? We can look at temperature and pressure resets. Humidity control, are we dehumidifying? Are we meeting that load? That sort of thing. Equipment staging, trying to make things as efficient as possible with the overall concept still in place. This is also a time where we start to look at specific shading devices. Maybe there's a room that has extreme loads that we need to deal with, and maybe we can set up an external shade that'll handle a lot of that. And once we're at this level, we're towards the end of the design process. Things are on paper and we're just about to send it out. We do sort of a virtual commissioning, and the LEED format has required us to do this for a number of years, where we look at unmet hours. There's Appendix G has a requirement on unmet hours. I believe it's 300 total. And so it really requires us to go into our models and see if there are any issues. And sometimes it's strictly a modeling issue. I put the wrong number into a certain box or whatever that might be. But sometimes it brings up errors in the design. For example, our airflow in a certain room isn't enough to meet the load. So that's something we can bring up with the designers and make that tweak before the building actually gets built and we get that cold call. So here's the final product. I showed you that example of the eQuest model where we were doing essentially the step-by-step. This is what it turned out looking like. Kind of this compromise of east-west and north-south orientations. So we met a lot of the massing goals we were aiming for, and maximize the PV area on the roof, south-facing roof. And we've been monitoring it for the last 5+ years to see what that performance is compared to what we expected. The solid line, or the blue line on top, represents the energy model data, what we anticipated from the building. The blue bars are the actual performance on a monthly basis. And so you see we predicted quite a bit higher usage than they actually ended up using. And the reason for that is mostly just the occupancy. And I think that's something that's often overlooked in these energy models, is just how the building is actually used. We make these assumptions that a school building is operated this way, an office is operated this way, but getting to know exactly what's happening in these spaces is important, and probably the biggest factor in building energy consumption. On the other side of the chart here, in the negative, we have our PV generation, and the yellow line represents our model, and the bars represent the actual PV generation. You'll see a couple spots here where we're not even close. And so when we saw that happen, we were able to contact the owner and say, hey, what's happening with your PV array? That we're not even close to what we expected. And it turned out they had blown a couple fuses in the system, and 2 out of their 3 arrays weren't generating any power. So we were able to call in the contractor and get that remedied. And since then, we've been holding pretty steady compared to actual. So then the green is the net difference. And for most months of the year, we're finding we're operating net zero and well below it. And then here's another example. This is a number of projects we've been tracking over the years and how they compared actual versus predicted. So the x-axis is our predicted, y-axis is actual. And for the most part, we have some pretty good correlations there, but some of our banks are ending up a little bit higher than we anticipated. and the grocery stores are ending up higher than anticipated. So it's time to kind of calibrate our assumptions and try to get back into that range where we'd expect them to be. All right, and then before we close here, I just want to drive home that when we're talking building performance, we're not just talking energy. There's a lot of other things that go into that, and one of those is thermal comfort. When we designed, this was a lobby we did. It's a glass box with a concrete wall, an uninsulated concrete wall. So we found that there's a good portion of that particular space that just isn't going to be comfortable. So identifying those spaces and working with the architect to come up with a solution is important. Daylighting, these guys here at the IDL are the experts here. There's all sorts of studies showing the benefits of daylight on performance. Damon has a great presentation on how that impacts student performance. Something to consider on most projects. And then working that daylight in with glare and views is important. Daylight's great, but if it's blinding you, that's not very helpful. And just being able to see out the window improves mood and performance as well. And can't really have a presentation on building performance without talking about the pandemic. Kevin van den Wijmelenberg has presented this at IDL and other places. He has a tool out now to assess your risk. So I'd encourage you to take a look and play with the little knobs on ventilation and filtration and the size of your space and all sorts of factors you can work into there to see what your risk level is. And then, of course, the ASHRAE resources, they've got great resources on how to work with that. But a lot of this is owner specific too, so make sure you know what your owner is hoping to accomplish. As far as trends I'm seeing out there, and it looks like we have some comments here, I think I'll open up the floor here shortly to share those, but the fixed baseline is something that's been kind of slow to progress, but I think there are a lot of opportunities there in terms of automating baseline simulations with a fixed baseline. And performance modeling seems to be growing. California's Title 24, they've been doing it a long time over there. The Washington State Energy Code has a new metric out there that is performance-based using the DOE's, blanking on the name, Building Asset Score. And the federal government has also used that as a standard for quite some time. So it seems like that industry is only growing. Energy metering is also getting to be more of a big deal, and comparing that energy data to actual data, and maybe even to the point where we have data-based models rather than simulated models. Automation, the BIM-BEM integration, Revit to whatever energy modeling software, or I think that'll continue to grow to the point where we have one model for everything. And then microgrids and renewables are starting to pop up all over the place, talking about source energy rather than site energy, which is what our codes are based on now. Source energy and embodied carbon tend to be, or are starting to become a bigger issue. Here's an example of OpenStudio's performance-based scripting. They're definitely not perfect, but they've got scripts to automate Appendix G baselines. At this point, to my knowledge, there are no 2016 automated baselines for OpenStudio yet. So we'll wrap it up here and then open up for questions. But the reasons I've been finding for performance path are value to the owner, building insulation, especially on the mass wall side of things. Windows, whenever we're over prescriptive window to wall ratios. Economizers show up a lot with in the age of dedicated outside air systems. And then anytime you're doing a green building certification, it's pretty easy to switch that documentation over. And I want to keep encouraging you that we can do better than legal buildings. Let's not just design to code here. Let's set some aggressive energy targets and see how we can do. and then follow that up with actual data. And more these days, we see the well standard and you know, the pandemic kind of influencing how we look at spaces. So let's look at building performance more holistically. Let's look at the health of the building, the daylight, the views, the comfort, and work that all into one thing. So with that, let's open it up to questions here. So I see from Michael Rosenberg, I'll just read this one. The ASHRAE compliance forms in the user's manual actually don't meet the documentation requirements that are listed in 90.1. The requirements will be updated in the new 2019 user's manual. P&L DOE recently released comprehensive compliance forms for Appendix G. Well, that's good to know. Thank you, Michael. I will check that out. And then IACC 2021 will include receptacle control requirements, basically the same as 90.1. Good to know. Are you guys seeing, I'd be interested to hear what else is going into IECC 2021. I haven't been up to speed on that.
There's a DOE webinar on that. I think it's next week. If you look at the energycodes.gov site, you'll see a list of upcoming webinars that take the place of what was typically the Energy Codes Conference that had to get canceled because of COVID-19. And I know that coming up very soon is a series on what the changes to the 2021 IECC are. I could look for the date while this is going on if you want, and put it in the chat window.
Yeah, that'd be great. I'll be looking for that. Okay. From Cheryl, made a good point early on. The project team needs to consider the long-term effects of not following prescriptive code. What are some model assumptions you need to make that impact these long-term effects? One example I think of is more glass and less insulation could mean uncomfortable occupants who plug in space heaters or operate heating systems different than design, resulting in more energy cost. Yeah, and that was really the one I had in mind too. It seems like often the prescriptive path is used for more glass, and you know, no matter how good your glass is, it's not as good as a solid wall. So there's energy increase from that, and definitely thermal comfort becomes an issue with any kind of significant amount of glass.
Tim, sorry, can you hear me?
Yeah.
So yeah, I'm just wondering, I'm not as familiar with, I guess, the mechanical and lighting sections. You know, by going to the performance path, are we similarly losing out or missing out on things through, you know, prescriptive requirements in the lighting and mechanical chapters?
Yeah, that's a good question. I think the one we typically get around is the economizers, like I mentioned, and there is a lot of benefit to economizers, but I've also been finding that the balance point of buildings is getting closer to that economizer range. So the benefit of economizers maybe not, or may not be as big as it used to be. You know, lighting loads have dropped significantly. So the heating load, or the cooling load in a space when it's relatively cool outside isn't as significant as it might have been in 10 years ago. Okay, and then Matt says one issue with 90.1 2016 plus is that the PRM baseline mechanical systems is determined by climate zone rather than heating fuel, which is causing conflicts with electrification initiatives. It's also caused issues for LEED 4.1 projects, which use 2016. Oh, that's a good point. Thanks, Matt. Okay, and then looks like, Michael, you shared the link to the webinar there. Appreciate that.
Right, and it's actually tomorrow.
Oh, okay. Great. Any other comments, questions, war stories?
Yeah, I had one more. What do you think about energy cost as a metric? Should we be considering other metrics? You know, you touched on a couple of them, but you know, for future code iterations, what do you think?
Yeah, that's a great question and a whole can of worms there. But you know, up in these northern climates, we definitely find that natural gas is a lot cheaper than electricity. And so if we're trying to compare any kind of electrified system to natural gas, it's pretty hard to justify. So changing that to energy would really change the game there.
So this is Mike Rosenberg again. So I've worked with several jurisdictions to help them customize the PCI BPF approach in Appendix G to address that issue. So Washington State recently in their code switched the metric to carbon emissions. New York uses both source energy as well as cost. LEED has emissions as a option. And Colorado is got a source energy metric in there too. So you're right, in places where electricity is expensive, it can conflict with some jurisdiction policies to electrify. And the 90.1 committee is actually thinking about maybe putting an informative appendix in to explain how Appendix G could be used with those different metrics to encourage those different policy goals. I also recently wrote a paper on it that was for the ACCC conference that touches on some of this.
Okay, great. Appreciate you guys jumping in and sharing your knowledge here too. I think Michael, you and Cheryl, I've seen on some of these forums and discussions and prescriptive or performance-based compliance before. Appreciate the insight. Well, thanks everybody for the opportunity. I think that was a great discussion, and there's a lot of interesting things heading our way in the world of performance-based compliance.